All right, so in this video, we want to start going through section 2.4. Um, so I'll just sort of point out a couple of things, off the bat. Um, so section 2.4 is about Riemann and Riemann integration, which we've already sort of discussed, but also about sort of an extension of this, which is called Riemann-Stieltjes integration. So this week, we're not going to get into Riemann-Stieltjes integration. We'll save that for next week. So sort of the plan is that I want to set up really in this video some of the background for Riemann integration, and some of this we've seen before. So for example, I'm not going to write out every definition, like specifically if you look at definitions 2.8 and 2.9 in your book, we've really already used more or less those definitions before when talking about Riemann integration. So I'm not going to write them out, but you may want to take a look at them and copy them down in your notes if you're sort of keeping notes in that way. But I thought it'd be helpful to just sort of illustrate a lot of this by looking at sort of a picture again and just remind ourselves of the general idea. So if I want to integrate a function using the Riemann integral on some interval a to b, then the first thing I'm going to need is I'm going to need a partition of that interval. So I'm going to take a partition of this interval. So that's going to be my partition P is just going to be some collection of points beginning with x0, where x0 is just a by definition, and then some points x1, x2, x3, and all the way up to, if I take a partition of n points, then my last point would be b. Okay. The first thing I'm going to do is I'm going to take a partition of my interval a to b, and you can think of these sort of in your Riemann sum as being the bases of each of the rectangles. Okay. Now, once I have that partition, I can sort of think about each of these little bases here. So in particular, let's say I was to look at the piece here between x2 and x3. I mean, I might ask myself sort of, I might want to refer to sort of this interval or the width of this interval. So in particular, I would call this delta x3. Okay, so it's always the upper one. So in general, we have that delta xk is just xk minus 1, right? So it's just the difference between the upper and the lower one here, okay? So there's sort of the width of that interval. But right, so that's good if I'm thinking about sort of constructing, rectangles. Okay, I have my base, but the question then is sort of what point on my function am I going to use between x2 and x3? And this is where we end up picking points called tags. Okay, so for example, I might choose a tag in here. So I'm going to call this C3. So again, in general, CK is the tag that lies in the closed interval x sub k minus 1 to x sub k. Okay, so I could choose C3 here, and this would give me sort of the height of my rectangle. And so when I go to compute my Riemann sum, sort of right, the rectangle would have this height. Okay, and so then, in general, if I start looking at Riemann sums, then I have the Riemann sum of some function given at partition P is just the sum for k equals 1 up to n of f of c sub k times delta x sub k. So right, it's just the height times the base. Okay, but this is a general form, right, that allows me to have sort of different bases for each of these rectangles. One thing that is going to be important as we start to talk about these, so if we want to talk about the Riemann integral, right, the idea is that we want to let the bases sort of get smaller and smaller, but they're all different sizes. Okay, so the way we normally do this is we talk about something called the norm of the partition. So if we have a partition P, we'll define the norm of the partition to just be the maximum of all the base lengths. Right? And so really the idea here is the norm of the partition is just whichever of these intervals happens to be the largest. So maybe here it's delta x3, okay? The idea is that if I let the norm of the partition go to 0, that means that the largest one is going to 0, which means all of the other ones also have to be going to 0. So this is again just sort of a generalization of stuff we've seen before. Okay. All right. Perfect. So this is all sort of the usual setup, but we want to start sort of building the theory of some of this. So let's sort of look at some other things here. So in particular, one thing we want to sort of look at are upper and lower sums. Okay. So if I take a given partition, and maybe I'm going to try and sort of stick with this partition here, right? So if I take a given partition, right, there are lots and lots of Riemann sums that I could come up with for this particular partition, and they would all be generated if the partition is fixed. And the only way to generate different sums is by looking at different tag values, right? But I mean, there are an uncountably infinite number of choices of tag values in each of these finite number of subintervals. So there's an uncountable number of possible Riemann sums you could come up with this, even for a fixed partition. So we want to look at two that sort of, and again, this is sort of a common idea in analysis, right? Let me sort of bound these things. So the idea is going to be to define sort of an upper sum and a lower sum, okay? So if I wanted sort of the smallest possible Riemann sum here, what would I do? Well, my delta x values, I mean, think about a Riemann sum, right? It's, let me switch pens here. Let's try this color. So think about a Riemann sum. Right, it's defined this way. If my partition is going to be fixed, then these values are fixed. There's nothing I can do to control those. Okay. So if I want to make these small, then what I need to do is I need to choose my C sub k's so that f sub k, or sorry, so that f of C sub k will be as small as possible. So for example, in this first interval here, right, I would look and I would say, well, what's the smallest function value in that interval? Well, I think that's it. And so I would pick this to be my C1. Okay. Similarly, I'd come over here and ask myself, okay, what's the smallest function value on this interval? And maybe here, that's also at this endpoint. So that would be my C2. Then I would come here to this interval, x2 to x3, and ask what's the smallest function value? And I think it's, again, here. So that would be my C3. Okay. So what I'm going to do is I'm going to define this lower sum to be just the sum k equals 1 to n of little m sub k times delta xk, where little m sub k is just the minimum value on the interval x sub k minus 1 to x sub k of f of x. Right, so I'm just picking the actual minimum function value on each of these, and then that gives me the height I want for this rectangle. Okay. Now, you can imagine again, what if I wanted to make this sum as large as possible? Well, I'm going to call this an upper sum. And I'm going to define it in a nearly identical way, but I'm going to put a capital M sub k of delta x sub k here, where, unsurprisingly, my capital M sub k will just be the maximum function value on that interval, x sub k minus 1 to x sub k. Okay. So these are technically, they're called upper and lower Darboux sums. I will often just sort of refer to them, especially if it's clear in context what we're doing, as upper and lower sums. And so we can sort of illustrate this nicely. So if we look, for example, on, say, this interval here. Okay. So what would a lower sum would look like? A lower sum would look like this rectangle in blue here. An upper sum, I would use the highest function value in this interval, right? So that would look something like this. That would look like sort of all of this in green. Okay. And then for any other tag value for any tag value you choose, you're sort of caught between this lower and upper sum, right? Any other Riemann sum that you might happen to take. So let's say you happen to take a Riemann sum and you took this value of C sub 3. Okay, then you would get a Riemann sum that's somewhere in between those two. Okay, so this is nice because these upper and lower sums sort of provide you some sense of, for a fixed partition, what's the largest my Riemann sum could be, what's the smallest my Riemann sum could be. Okay, so I mean this is really useful, even though maybe it seems very simple right now. And I'm going to have you look at and sort of examine some properties of these upper and lower sums. So it turns out even as you change the partition, some nice sort of things happen here. Okay, so sort of looking forward, we can use these upper and lower sums to help us sort of talk about when a function is or is not Riemann integrable. Okay. So we just want to get a couple more definitions here. So my goal really for this video is to get all the definitions out. We'll come back later and then see how we can combine all these definitions to get a lot of theoretical results. Okay. So I now have these upper and lower Darboux sums. Okay. And let's see, I have another black marker somewhere. Oh, it's under my iPad here. All right. So since I have these upper and lower sums, right, and normally you have a Riemann sum, you use a Riemann sum to define a Riemann integral. Now I have these upper and lower sums, I can use these upper and lower sums to define upper and lower integrals, okay? And it's sort of analogous to what we do for Riemann sums, to Riemann integrals. So this is definition 210, so if I have a function f from AB into the real numbers, which is bounded, then we define the upper and lower Riemann integrals to be, all right, so if I want start with the upper. So the way this would be like the normal Riemann integral, the way we denote that this is the upper is we put a bar up here above the integral sign. So this is the upper Riemann integral from a to b of f of x dx. So this is going to be the infimum over all partitions P of the upper sums. Okay, so this is a little tricky, but we'll draw some pictures in here in a minute to help understand. Okay, and we also need to define our lower Riemann integral. So similar notation, so integral from a to b, but this is a lower one. I put a bar at the bottom of the integral sign of f of x dx. This is going to be the supremum over all partitions of, sorry, I guess I was using a curly L, of the lower Darboux sums. Okay, so sort of what's going on here? So again, you imagine you have some function on the interval a to b, and it's going to be bounded in. And since I'm drawing this, let me just draw. I'm even going to draw a nice continuous function just to understand this first. So here's my thing. Okay. Now let's first just look at upper sums. Okay. So when I'm looking at an upper sum, okay, so I take some partition, and now in each interval, I look at the highest point and use that to construct my rectangles. Okay, and so maybe the highest point here, there, and there. Should have maybe made this function a little less flat, but you get the idea here. Okay. So there is an upper Darboux sum. And again, for this partition, there's only one upper Darboux sum, but now I could start changing the partition. And so that's really what this is saying. So as I start changing the partition, there's sort of a couple ways I could change it. I mean, one would be I could move the points around, but another thing is I could start adding in other points, right? And this is really sort of the natural idea that we sort of saw in calculus, right? Is that you would increase the number of rectangles. Okay, so you can sort of think about, what happens if I add a point in here? So what happens if I came here and I just added another point into my partition? Well, now these two rectangles are going to be split up. Okay, and if let me leave the rectangle that was already there. Let's sort of see what happens here. So now I would look on this interval and choose the largest point. And then I would look on this interval and choose the largest point. And so maybe this is a little hard to see on webcam, but actually what's going to happen is just by adding a point into my partition, I now have a slightly smaller upper sum. As you can see, right, this little bit is missing here. This is no longer in my blue rectangle here. So like this in green is missing. So it turns out, and this is one of the things I'm going to have you prove, that as you add more points to your partition, the value of your upper sum is going to be non-increasing. I mean, it's actually possible it could stay the same, but it in all likelihood may come down also. So what I want to ask myself is not sort of what is the upper sum for a fixed partition, but if I look at every possible set of partitions of this interval, what is the infimum of that set, right? And so what's the infimum? It's sort of, it's by definition the greatest lower bound, right? So I want to look at sort of what's the level that I can never get below by taking these sort of upper sums. And that's what I'll call my upper Riemann integral. Similarly, we can do the same thing for lower integrals. So in that case, you see that as you add points to your partition, actually the value of the integral can increase. And so you want to know what's the supremum over all the possible partitions there. Okay, so there will be opportunities to sort of explore this in the exercise set. Unsurprisingly, the result that you end up with is that a function is Riemann integrable. Okay, well, and I shouldn't say the result you end up with. This is sort of how we end up defining then Riemann integrability. Erase here. So definition, a function f from AB into R, which is bounded, is Riemann integrable if and only if the lower Riemann integral is equal to the upper Riemann integral. Sort of if, as you take those upper sums and lower sums and you refine those partitions over and over again, if those upper sums and lower sums are converging to some common value, that means the upper and lower sums are equal, then we say that the function is Riemann integrable. And okay, well, if this is equal, that means the function is Riemann integrable. And then we just define the value of the Riemann integral, which we write a to b of f of x dx to just be equal to, so let's say this value had, what was the value, I, then we'll just say the value of the Riemann integral is I. Okay. So again, this is sort of the natural generalization of what you saw in calculus, where we're no longer requiring sort of evenly spaced partitions. We're no longer sort of, we're allowing a more general set of behaviors, but we still want to capture this idea sort of that as we refine that partition, as the number of rectangles gets larger and larger and larger, we really should have sort of these upper and lower Riemann sums, or upper and lower Darboux sums, converging to some common value. And if so, that'll be the value of our integral. Okay. So I'm going to stop there. And there'll be, again, problems in the exercise sets for you to play around with some of the definitional pieces here. And then next week, what we'll do is we'll come back and we'll really start digging into, okay, now that we understand all these moving pieces, how do we start proving properties of Riemann integrals? And then we'll see how to extend the Riemann integral to the Riemann-Stieltjes integral.